So welcome to my modelling project on populations, which we're going to finish off now with the third cycle of our iteration, model number 3. I'm kind of happy enough really with my model 2 solution. It's what we call a continuous solution based on a differential equation. And you can see that the population starting in the year 2010, over the decades, it gradually goes towards a carrying capacity of 12 billion in a nice smooth fashion. I was going to then apply that particular solution to a city, a thriving city with a great labour market where people are pouring into the city to avail of the job opportunities. And I didn't think this model quite worked for that situation. Obviously, the city will have a carrying capacity as well, eventually, given its infrastructure, that it can only take in so many people. But I don't see people behaving like this. I don't see people gradually moving towards the carrying capacity. I can see a situation where people behave erratically. They pour into the city, they overshoot the carrying capacity, then apartment rentals go too high and they have to leave, and then prices readjust and more people come in. I kind of see a situation when it comes down to people with a rapidly growing population. I can see them kind of zigzagging or oscillating about that carrying capacity. So I wanted to capture that kind of behavior in my third solution, my model 3 solution. This is called a discrete solution using difference equations. I'm going to turn that differential equation into a difference equation. Instead of the change of population with time, I'm going to write down Pn plus 1 minus Pn. In other words, that's the difference between two populations separated by a decade. And that's equal to K times Pn times 1 minus Pn divided by K, capital K, the carrying capacity. And then let me just jump that Pn term across. So now here's my differential equation. Pn plus 1 is equal to Pn plus K. That's the growth per capita. Pn times 1 minus Pn divided by the carrying capacity of K. So I'm going to use that difference equation now to talk about my city. So let me go on to the next board here. There's my new discrete difference equation. Pn represents the population at the end of a decade N. Now, what numbers am I going to use? Well, it can be any city you want. So in one sense, I can make up the numbers, which I'm going to do. And for simplicity, I'm going to use many of the numbers that I used in the previous two models. Except I wouldn't expect a city to have a population of billions. So I'm going to change the billions to millions. So let's say the starting population of my city is 6.83 million. Its carrying capacity, let's say, is 12 million. And this time, you see that growth per capita? It was 0.144 when we did the human population growing on the Earth. But I've got a situation here where I've got a rapidly growing population in a city where people can pour into the city and increase the population rapidly. So I'm going to do a 10-fold increase in K. I'm going to turn that into 1.44 and see what happens. There's my difference equation. I'm going to fill this table in for the first 9 decades. And then I'm going to draw a graph and see, does it simulate the kind of human behavior that I would expect of the population in a city. Let me manually work out the first 2 entries in my table so you get a bit of a feel for that difference equation. And then I'm going to go back to Wolfram Alpha to generate the rest of them because I couldn't be bothered putting them all into my calculator. But let me work out the first 2. I've got P0, which I filled in as 6.83 million. Let me now work out P1. So P1, the population of my city after 1 decade, is Pn. So I'm going to let n equal to 0 to get P1 there. That's P0 plus K times P0 times 1 minus P0 divided by big K. Put my numbers in there. P0 is 6.83 plus K times. The growth per capita is 1.44 by P0, 6.83 times 1 minus P0, 6.83. And the carrying capacity for my makeup city is 12 million. So let me put all that into my calculator. And when I do that, I get an answer of 11.07 million to 2 decimal places. So let me put that into my table. After 1 decade in my rapidly growing city, the population is now 11.07. So you can see it's a massive increase in population. Let me do one more. Let me work out P2. So P2 is equal to P1 plus K times P1 times 1 minus P1 divided by K. So that's equal to P1 is 11.07 plus K times 1.44 times P1, 11.07 times 1 minus P1, 11.07 over the carrying capacity of 12. So let me now put that into my calculator. And when I do that, I get 12.31 million. You can see it's overshot the carrying capacity 12 million, which is what I kind of expect from erratic human behavior. You know, you get that kind of gold rush effect, and then suddenly people are in there and they find that they can't afford the the apartment rentals, and they have to leave, and then everything readjusts, and we get that kind of zigzagging look to the population of that city. So let me fill this in. This is 12.31 million. So I want you to generate the rest of the results from Wolfram Alpha. So I've put in the code for this. You can copy and paste this code from your notes if you wish, or write it in yourself. I've put in that difference equation into Wolfram, and I've written down that P0 is 6.83, and now I'm ready to generate all my solutions. I get a graph there. My graph isn't very clear. I'm going to actually draw that graph myself. Here's the values here: 6.83, 11.007. Let me generate more results by pressing more here. So there's the results, let's say, for the first 9 decades written down there. So let me take those results and put them into my table. And I want you to do this in your notes. So if I go back to my notes, there's all the results in the table. It's 2 decimal places. And I actually want you to draw your the graph yourself. It's going to be a little bit more clear, and it's going to be more educational anyway when you draw the graph yourself. So let me go back to the board here. There's all my results put in. Here's my graph here. Here's time in decades and population in millions. So my first result is at the beginning, which I think was 2010. My population in my city is 6.83 million. So let me put that point in. After 1 decade, it's 11.7 million. After 2, it's 12.31. And so on. So keep on putting your points in, and they're gradually merging towards a carrying capacity of 12. So now I'm ready to draw my graph. It's a discrete graph. So just join the points here. So it's going to go up like this, and then it kind of zigzags around the carrying capacity. And eventually the zigzagging is so minute that it actually merges into that line there. So that kind of graph there is probably more realistic in terms of talking about the erratic behavior of people moving into a city where there's great opportunity. It kind of zigzags or oscillates about the carrying capacity until over the decades it will settle down. Okay, so I've done my 3 iterations in my modeling cycle. That's the heart of the project. It's not a full project, by the way. It's only outlining, sketching how you would go about doing a project. And then you've got to interpret the results for 15 marks. And this is just some of my conclusions. Again, it's very sketchy, very brief, not a full project. So what I said was model 1 works very well for small populations with unlimited resources over a short time. Then the continuous model 2, that gives good results for the growth of a large population over a long time where we have a finite carrying capacity. And then the last model I did, the discrete model 3, seems to give a more realistic solution to rapid growth of population in a city where people gradually approach the carrying capacity in an oscillatory or zigzag fashion in response to reducing resources. And my reflections are, after completing my project, I've come to appreciate the extent to which mathematics is relevant in everyday life. Again, very brief, it's just trying to give you an idea. Okay, so that's the end of my modeling project. I hope you got something out of it. I want you to do your own project. You've got plenty of time to do it, so enjoy.